splicing 500 MCM conductors to 23/0 cables can be National Electrical Code compliant, provided certain conditions are met. These conditions primarily revolve around conductor ampacity, the splicing method employed, and the enclosure used to house the splice. Firstly, the ampacity of the 3/0 cables must be equal to or greater than the ampacity of the 500 MCM conductors. This is a critical requirement to ensure that the conductors can safely carry the intended current without the risk of overheating, which could lead to insulation damage and potentially a fire hazard. The appropriate ampacity can be determined using the National Electrical Code Table 310.15b16 or other relevant tables considering the conductor's insulation type and the ambient temperature. Secondly, the splice itself must be executed using an approved method. Acceptable methods typically include mechanical splices or compression terminals. Regardless of the chosen method, the splicing connector must be specifically rated for the size and ampacity of the conductors being joined. Using an incorrectly sized or underrated connector could result in a loose connection, leading to arcing, overheating, and ultimately failure of the splice. Thirdly, the splice must be enclosed within an approved junction box or conduit body. This enclosure serves to protect the splice from physical damage, environmental factors such as moisture or dust, and accidental contact. The enclosure must also meet all relevant requirements for the chosen splicing method and the insulation rating of the conductors. The National Electrical Code provides detailed specifications for junction box sizing and conduit body selection, depending on the number and size of conductors being enclosed. The rationale behind allowing the use of parallel conductors, such as the two 3/0 cables in place of a single 500 MCM conductor, lies in the principle of increasing the overall ampacity of a circuit. By using multiple conductors in parallel, the current is distributed across each conductor, effectively increasing the circuit's capacity to carry current. In a scenario where 3/0 cables are used to provide an equivalent ampacity to a 500 MCM conductor, the smaller cross-sectional area of the individual 3/0 cables can be advantageous, particularly in situations where space is limited or where greater flexibility is required. Furthermore, the relatively short distance between the current transformer cabinet and the switchgear can justify the use of smaller conductors, as the voltage drop over this distance will be minimal. However, several additional considerations must be taken into account to ensure the safety and reliability of the installation. Firstly, it is essential to verify that there is adequate wire bending space within the switchgear and conduits to accommodate the 3/0 cables and their associated splices. Insufficient bending space can make it difficult to properly install the conductors, potentially leading to stress on the insulation and increasing the risk of damage. The National Electrical Code provides specific requirements for wire bending space in enclosures, based on the size and number of conductors. Secondly, it is crucial to calculate the current in each parallel conductor to ensure that the current is balanced. Uneven current distribution can lead to some conductors carrying a disproportionately high share of the total current, resulting in localized heating and potentially premature failure. To ensure balanced current, the parallel conductors should be of the same material, have the same length, have the same insulation type, and be terminated in the same manner. Thirdly, if current transformers are being used for metering or protection purposes, the current transformer ratio and the accuracy of the measurement must be carefully considered when using parallel conductors. The current transformer ratio must be selected to accurately measure the total current flowing through the parallel conductors, and the accuracy of the current transformer should be verified to ensure that the metering and protection systems function correctly. As an alternative to using parallel conductors, particularly in situations where space limitations are a significant concern, extra flexible conductors rated for the required ampacity could be considered. These conductors are designed with a higher strand current, making them more flexible and easier to bend and fit within confined spaces. However, it is important to ensure that these extra flexible conductors are properly terminated using appropriate connectors and that they meet all other applicable National Electrical Code requirements. The selection of conductors, splicing methods, and enclosures should always be based on a thorough understanding of the electrical system's requirements, the applicable codes and standards, and the specific environmental conditions. Consulting with a qualified electrical engineer or inspector is highly recommended to ensure that the installation is safe, reliable, and compliant with all applicable regulations. In more detail, let's discuss ampacity considerations. Ampacity, a portmanteau of ampere capacity, is the maximum amount of electrical current a conductor can carry before sustaining degradation. It's determined by several factors, primarily the conductor's material, size, insulation type, and the surrounding ambient temperature. Copper and aluminum are the most common conductor materials, with copper generally having a higher ampacity for a given size due to its superior conductivity. The cross-sectional area of the conductor, typically measured in circular mils or thousands of circular mils, denoted as MCM, directly affects its ampacity. A larger conductor has a greater surface area for heat dissipation, allowing it to carry more current without overheating. Insulation type plays a critical role in determining ampacity. Different insulation materials have varying temperature ratings, indicating the maximum temperature the insulation can withstand without breaking down. Common insulation types include THHN, THWN, XHHW, and others, each with different temperature ratings and suitability for specific environments. The National Electrical Code Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types, assuming specific ambient temperature conditions. Ambient temperature, the temperature of the surrounding environment, also affects ampacity. Higher ambient temperatures reduce a conductor's ability to dissipate heat, thereby lowering its ampacity. The National Electrical Code provides correction factors to adjust ampacity ratings based on ambient temperature. When splicing 500 MCM conductors to 3/0 cables, it's imperative to ensure the combined ampacity of the 3/0 cables equals or exceeds the ampacity of the 500 MCM conductor. This ensures the circuit's overall current carrying capacity is maintained. For instance, if a 500 MCM copper conductor with THHN insulation has an ampacity of 380 amps at 30 degrees Celsius ambient temperature, the combined ampacity of the two 3/0 copper cables with THHN insulation must be at least 380 amps. Each 3/0 copper conductor with THHN insulation typically has an ampacity of 200 amps at 30 degrees Celsius, so two in parallel would provide 400 amps, satisfying the requirement. Now let's look at acceptable splicing methods. Splicing involves joining two or more conductors to create a continuous electrical path. The splicing method must ensure secure, reliable connection with minimal resistance to prevent overheating and voltage drop. Several approved splicing methods are commonly used, including mechanical connectors, compression connectors, and exothermic welding. Mechanical connectors, also known as set screw connectors, use mechanical force to clamp the conductors together. These connectors are relatively easy to install and require minimal specialized tools. However, they may be more prone to loosening over time due to vibration or thermal cycling. Compression connectors use a crimping tool to compress the connector onto the conductors, creating a tight, permanent bond. These connectors offer excellent conductivity and are less likely to loosen over time compared to mechanical connectors. However, they require specialized crimping tools and dies specific to the connector size and type. Exothermic welding, also known as CAD welding, involves using a chemical reaction to melt and fuse the conductors together. This method creates a highly reliable, low-resistance connection that is resistant to corrosion and vibration. However, it requires specialized equipment and training, and the process is irreversible. Regardless of the chosen splicing method, the connector must be listed and labeled for the specific conductor sizes and materials being joined. The connector's voltage and temperature ratings must also be appropriate for the application. The National Electrical Code Section 110.3b requires that all electrical equipment, including connectors, be installed and used in accordance with their listing and labeling. Proper installation techniques are crucial for ensuring a reliable splice. This includes stripping the insulation to the correct length, cleaning the conductors, applying antioxidant compound if required, and tightening or crimping the connector to the manufacturer's specifications. Over-tightening can damage the connector or conductors, while under-tightening can result in a loose connection. Splicing must be performed in an accessible location, as splices cannot be concealed within walls or ceilings without a junction box. This allows for inspection and maintenance of the splice. Junction boxes and enclosures. Enclosures such as junction boxes and conduit bodies are essential for protecting splices and providing a safe, accessible location for connections. The enclosure must be appropriately sized for the number and size of conductors and splices it contains, with adequate space for heat dissipation and wire bending. Junction boxes are typically metal or non-metallic enclosures used to house electrical connections. They come in various sizes and shapes, and they may be surface-mounted or recessed. The National Electrical Code Article 314 provides detailed requirements for junction box sizing and installation. Conduit bodies, also known as conduits, are fittings used to provide access to conductors within a conduit system. They come in various shapes such as L, T, and C, and they allow for pulling conductors, making splices, and changing direction of the conduit run. Conduit bodies must be sized appropriately for the number and size of conductors they contain, and they must be installed in accordance with the National Electrical Code Article 314. Enclosures must be listed and labeled for the intended use, and they must be suitable for the environment in which they are installed. For example, in damp or wet locations, enclosures must be weatherproof or rain-tight. Metal enclosures must be grounded to provide a path for fault current, while non-metallic enclosures do not require grounding. The National Electrical Code Section 314.40 requires that all junction boxes be securely fastened to a supporting structure. This prevents the box from being dislodged or damaged, which could expose the electrical connections. The enclosure must be accessible after installation, meaning it cannot be permanently covered or obstructed. This allows for inspection and maintenance of the splices and connections. When selecting an enclosure, consider the number and size of conductors, the splicing method used, the environmental conditions, and the accessibility requirement. A properly selected and installed enclosure will protect the splices, ensure electrical safety, and facilitate future maintenance. Parallel conductors and current balance. Using parallel conductors involves connecting two or more conductors together at both ends to form a single electrical circuit. This increases the overall ampacity of the circuit, allowing it to carry more current than a single conductor could handle. The National Electrical Code Article 310.10h provides requirements for using conductors in parallel. Parallel conductors must be the same material, have the same length, have the same cross-sectional area, have the same insulation type, and be terminated in the same manner. This ensures that the current is evenly distributed among the parallel conductors. Uneven current distribution can lead to some conductors carrying a disproportionately high share of the total current, resulting in localized heating and potentially premature failure. To ensure balanced current, the parallel conductors should be installed in close proximity to each other. This minimizes the impedance difference between the conductors. The National Electrical Code requires that parallel conductors be sized no smaller than 1/0, except under certain conditions. This is to ensure that the conductors have sufficient mechanical strength and ampacity. When using parallel conductors, it is important to calculate the required ampacity of each conductor. The total current is divided equally among the parallel conductors. For example, if a circuit requires 600 amps and two parallel conductors are used, each conductor must be sized to carry at least 300 amps. The overcurrent protection device, such as a circuit breaker or fuse, must be sized to protect the parallel conductors. The overcurrent protection device should be sized no larger than the ampacity of the parallel conductors. When terminating parallel conductors, it is important to use connectors that are listed and labeled for use with parallel conductors. These connectors are designed to ensure a secure, reliable connection that distributes the current evenly among the conductors. Wire bending space in enclosures. Wire bending space refers to the amount of space required within an electrical enclosure to properly bend and terminate conductors. Adequate wire bending space is essential for ensuring that conductors are not subjected to excessive stress or strain, which could damage the insulation and lead to electrical faults. The National Electrical Code Article 312 provides detailed requirements for wire bending space in enclosures. The required wire bending space depends on the size of the conductors, the type of enclosure, and the location of the terminals. The National Electrical Code provides tables that specify the minimum wire bending space for various conductor sizes and enclosure types. When determining the required wire bending space, it is important to consider the radius of the bend required for the conductors. The bending radius should not be less than the minimum radius specified by the conductor manufacturer. Insufficient wire bending space can make it difficult to properly install the conductors, potentially leading to stress on the insulation and increasing the risk of damage. It can also make it difficult to access the terminals for maintenance and testing. When selecting an enclosure, it is important to choose one that provides adequate wire bending space for the conductors being used. If the enclosure is too small, it may be necessary to use a larger enclosure or to use conductors with a smaller bending radius. The National Electrical Code requires that conductors be installed in a neat and workmanlike manner. This includes properly training and bending the conductors to fit within the enclosure without putting excessive stress on the insulation. Current transformer considerations. Current transformers, or CTs, are used to measure alternating current in electrical circuits. They are typically used in metering, protection, and control applications. Current transformers operate on the principle of electromagnetic induction. A primary conductor carrying the current to be measured is passed through the core of the current transformer. The current in the primary conductor induces a current in the secondary winding of the current transformer. The secondary current is proportional to the primary current, with the ratio between the two currents known as the current transformer ratio. The current transformer ratio is typically expressed as a ratio such as 100 to 5, meaning that 100 amps in the primary conductor will produce 5 amps in the secondary winding. The secondary current is then measured by a metering or protection device. Current transformers must be selected based on the maximum current they are expected to measure. The current transformer ratio must be chosen to provide an appropriate secondary current for the metering or protection device. The accuracy of the current transformer is also important. Current transformers are typically rated for accuracy, with higher accuracy current transformers providing more precise measurements. When using parallel conductors, it is important to ensure that the current transformers are properly installed and connected. The current transformers must be installed on each parallel conductor, and the secondary windings must be connected in parallel. This ensures that the total current is accurately measured. The National Electrical Code provides requirements for the installation and connection of current transformers. Alternative solutions to parallel conductors. In some situations, using parallel conductors may not be feasible due to space limitations or other constraints. In these cases, alternative solutions may be considered. One alternative is to use a single conductor with a higher ampacity rating. This may require using a larger conductor size or a conductor with a higher temperature rating. Another alternative is to use busbars. Busbars are rigid conductors that are typically made of copper or aluminum. They offer a high ampacity rating and can be used in place of multiple parallel conductors. Busbars are commonly used in switchgear and panel boards. A third alternative is to use liquid-cooled cables. Liquid-cooled cables use a circulating liquid to dissipate heat, allowing them to carry a higher current than conventional cables of the same size. Liquid-cooled cables are typically used in high-current applications, such as in power plants and industrial facilities. A final alternative is to redesign the electrical system to reduce the current requirements. This may involve using more energy-efficient equipment or distributing the load more evenly. The selection of the appropriate alternative solution depends on the specific requirements of the application. Factors to consider include the current requirements, the space limitations, the cost, and the reliability requirement. By carefully considering these factors, it is possible to select an alternative solution that meets the needs of the application. Remember to consult with a qualified electrical engineer. Consulting with a qualified electrical engineer is highly recommended when designing or modifying an electrical system. Electrical engineers have the knowledge and experience to ensure that the system is safe, reliable, and compliant with all applicable codes and standards. Electrical engineers can perform calculations to determine the appropriate conductor sizes, overcurrent protection devices, and other electrical components. They can also help to identify potential hazards and recommend solutions to mitigate those hazards. Electrical engineers can also provide guidance on the installation, testing, and maintenance of electrical systems. In many jurisdictions, electrical work must be performed by licensed electricians under the supervision of a qualified electrical engineer. Consulting with an electrical engineer can help to ensure that the electrical work is performed safely and correctly, and that it meets all applicable requirements. The National Electrical Code is a comprehensive set of standards for electrical installations. It is updated every 3 years, and it is essential for anyone working with electrical systems to be familiar with the latest edition. The National Electrical Code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is used by electrical inspectors, contractors, engineers, and other professionals to ensure that electrical systems are safe and compliant. State and local codes are essential to follow. In addition to the National Electrical Code, many states and local jurisdictions have their own electrical codes. These codes may be more restrictive than the National Electrical Code, and it is important to be familiar with them. State and local codes are typically enforced by electrical inspectors who ensure that electrical installations meet all applicable requirements. Electrical permits are often required for electrical work. Obtaining the appropriate permits can help to ensure that the work is inspected and approved, and that it meets all applicable codes and standards. Failure to obtain the required permits can result in fines, delays, and even legal action.